Right.
Most students here are new to quantum computing, right?
Yeah. Yes,
Okay.
I believe so. So welcome everyone. So this is now being recorded. This is our quantum computing workshop via comics, delivered by Kitty from Microsoft. So Kitty is tuning in from Germany, and we've got about an hour and a half of this workshop. So this workshop will be made available to everyone who wasn't able to join us, and we will make this link available for anyone else who would like to share. So Kitty, thank you so much for joining us. And it's all over to you now. Thank you.
Thank you so much, Elena, for having me here. And hello, everyone. Really nice to meet you virtually. And it's a great honor to be speaking with you about quantum computing. And I know that this is new to most people, and we're going to do a short or compressed workshop. Is kind of a crash course to let you know some of the key concepts that's involved with quantum computing. Just a little bit of my background. I am working with Microsoft right now, so I'm a physicist. I started my professional journey in University of Cambridge, where I did my master's and bachelor degrees. And I worked with the Cavendish lab on condensed matter physics, so called low temperature experimental physics, studying the quantum properties of materials. And back then there wasn't really a quantum computing industry. And we were starting more the fundamentals and building these lab equipment to put the samples in and study them at really low temperature in order to study the quantum behaviors. And that was a really good experience. And now it becomes very useful for me now. And then I moved to Harvard to do my PhD, and there I was doing more of the applied physics, and I made a lot of new circuit structure components and fabricated them in the clean room and built these nanometer and micrometer sized chips. And that was very useful for industry. When I graduated, I moved to Intel to work on silicon photonic chips. So that's a very similar fundamental property of nature you can use. You can fabricate on chips, and then you can guide light on your chip and use it for communication. So those were used in data centers, but I also work on some really fun projects for the Maker Group and did wearable technology. So that's another area that I'm really passionate about, is open source and wearables and fashion design with technologies. Then I had my own company, my own fashion brand called Art by a Physicist. This is a fashion brand that focuses on nature and science, and also made all these new type of wearables with my paintings on the fabrics, and put the electronics into the clothing so they can sense environment and they can respond. That was great fun. All of my past experience then became very valuable for what I'm doing now at Microsoft, is quantum computing, and I focus on quantum computing education because this is a really new field, industry area. It needs a lot of communication and education for the public or anyone with any background. We have people from academia, students like you, hobbyists, and industry professionals. They're all very interested in this topic, and we need to produce helpful materials to train people, to get people understand this new technology, because this is the next generation of computation. And this, and also my side projects, all allow me to pursue some of these global goals on the right here. Especially quality education here is very, very important. As you're participating in teams in AI, you all understand that the extra amount of work doing research and working on your own projects for your own learning, but also making impact for the society. So I use art to do science and use science to do art. So today's class, I will be showing you a lot of drawings that I use to explain quantum computing concepts. And I'm really interested in combining science, engineering, design, and art. And I think that is how we would generate things that people would understand and help us create culture. So a brief overview and an introduction. Since most people are new to quantum computing, let's just zoom out a bit. Our world is running on computers. The very reason that we can talk to each other right now is because of technology and internet connectivity and computers and all of these data centers that's connecting people and things, and we're trying to make everything smart. And without technology, we wouldn't be able to have this kind of connectivity. And we rely on machines to build our infrastructure and society. We have these supercomputers or high performance computer clusters that are sitting somewhere obscure and highly secured data centers that allow us to connect to each other, and we upload data there, and we can have these supercomputers to do tasks that our own PC would not be able to do. But even the most powerful supercomputers run into problems with some of the tasks, very heavy duty tasks. For example, there are intrinsically quantum mechanical problems. For example, chemistry simulations and materials. If you want to come up with a new type of drugs or invent a new type of materials for your applications, you would then get down to the microscopic level to really understand the structures and behaviors of molecules, of electrons, photons on your materials. And sometimes you have to simulate them, and some tasks are really heavy and very difficult to do with our current computation methods. And there are also problems that are more like man-made, less of the nature-made problems, such as logistics and cryptography, information security, or data processing. These things are themselves running on classical computer, and they are classical problems, but then we can get inspired from nature, from how quantum computer works, in order to apply onto them and perhaps run them as quantum algorithms using a new type of computation method. So there are a lot of applications for quantum computers to solve difficult problems that our fundamental, our classical computer run into fundamental limitations. In a way, quantum computing is like biomimicking. I like to show people these pictures where we as humans invent machines and we get inspired by nature. We look at animals and we make things that would imitate nature. And quantum computing is the same. Quantum computing is looking at the fundamental building blocks of our world, our universe, at the really small level, and trying to mimic it and build a computation method based on how our nature innately behaves. So we think that for some of the problems that our classical computers run into could be solved by this new way of computing. How does it work then? Before we go into the details, a lot of people ask me how they can get started with quantum computing. And there are a lot of materials already existing online. Some of them are very good, but there are also hypes and a lot of exaggerated claims about quantum computers. So we have to be able to distinguish what's believable. Like one of your teams is working on fake news. We have to be able to really understand how quantum computing work to really say where we are and how we can use it and where it is going to be useful. It's not going to be replacing all of our classical tasks because it could be overkill. But for certain tasks, they are very good. And we need to be able to understand some concepts. Namely, you don't need a lot of physics to do that. You actually just need to understand 3 key concepts called superposition, interference, and entanglement. We're gonna explain next what they are. And you need a little bit of maths. It's linear algebra. You probably all learned it in school, and it's not really hard maths. So you just need a little bit in order to know how you can manipulate the quantum bits and how do you construct algorithms using these concepts. And these little cards I draw that's connecting all these areas is our quantum computing language. If you are building a piece of hardware that's a new type of computer, then you need to have a new language in order to program it. And we have a Q# language that we can use. And later on, we're gonna do some hands-on exercise. We'll use Q# to familiarize yourself with these concepts. So with these, you can quickly write algorithms that could then run on the quantum hardware. I would touch upon a lot of these concepts in today's workshop. We'll spend more time on these concepts and the little bit of linear algebra, how to see how quantum computing works. And then I will show you some examples of algorithms and what types of hardware we have. So this is a nice journey is for you to get started from here, but we can use the language to help you get quickly started. And also a few words about really understanding and learning is that especially physics related subjects, we need to be able to describe our universe with equations, how things work, how we construct things on Earth. But we need to be able to also translate the equations into words to really understand it, to express it. But it also helps if we can condense words into drawings, but then use equations to describe the drawing. So this is like, I call this the trinity for understanding for any subject, really. If you really want to test your understanding, you can try, you need to have all 3. You need to be able to figure out what you actually do not understand while you try this exercise. And drawing is especially very important in physics. You don't have to be an artist, but then if you want to express your thinking using some sketches, you will quickly find out what are the weak areas that you may still have and be able to then learn more to build your understanding. And luckily, we also have coding that can help us be more practical to express some of the equations or your understanding into algorithms using code that we're gonna learn. So this is for you a trinity for learning here. So let's start with the 3 key concepts: superposition, interference, and entanglement. You probably heard of these terms at some point if you look up any discussion about superposition. But today we're going to really look at the fundamental, what exactly are these things. Let's look at first how our classical computers are built. We know that right now, when we are expressing information, we use zeros and ones. These are our bits. And there are many different ways to represent information and number, but we resolve down to this binary system where you can represent everything with zeros and ones. And fundamentally, we use transistors to do that. Transistors are just very, very tiny switches. It can be on and off, so it's zeros and ones. You find them in every electronics, our computers, our phones, and anything that's you plug into electricity, they have transistors in them. So classical bits are just zeros and ones. For example, like the transistor is a tiny switch. If you have this light on and off, you can call it zero, on or zero. Or if the temperature is too high or too low, you can also represent it in this binary system. Or you flip a coin, it has the head side and the tail side. You can also call it zeros and ones. Mathematically, we can express them as vectors. A 2x1 vector, and 0 will be, this is a state, classical bit. 0 will be 1 and 0, and 1 will be 0 and 1. And there's no other possibility. You just have these two numbers, and if you express them with this vector, then you have only these two options. Again, I mentioned transistors. This is how you can build them in actual material. We're gonna talk about the hardware at the very end, but here is just showing you transistors are made of semiconductors, and you have some insulators and some metal gates on top. So it's a sandwich of different materials. You can control with the gate, with the voltage applied to your material. If you apply certain voltage, it will have electricity from source to drain. Then that could be your on state, and we can call it 1. You can also have certain electricity or voltage that doesn't allow electrical current to go through. That will be your off, and you can call it 0. That's how we do it in classical computing. But you don't have to do it that way. It's kind of using a switch binary model is like a pretty simplified version of how nature behaves. Because why do we just have two and either or? We could have situations where if you look at our fundamental building blocks, atoms, electrons, photons, they could have different energy levels. If you study any physics or chemistry at all, you probably heard of the orbitals and energy levels for electrons to occupy in an atom. And all of these energy states, they can coexist and they can be in a combination. And we have a word for it, it's called superposition. All of these levels for your nature, for your quantum particle to occupy can have a superposition of all these options that they can be on. And for each energy level, they have a certain probability of being there. And we can use that for computation. Now we look at the difference between classical bits and quantum bits. If you have a classical case, like I showed earlier, like a binary situation, you can draw any of these analogy. Like if you have a circle that is empty, you can call it 0. If it's filled, you can call it 1. That's a classical bit. But quantum bits are allowing you to have both the 0 and the 1. And in this case, you can fill you can fill 2/3 of it. Then you will have 1/3 of 0 and 2/3 of 1. You could have this lottery ball that has a lot of beads in them, say 20 of them. If they're all 0, you can call it 0. If they're all red, you can call them 0. If they're all blue, you can call them 1. But then in the quantum case, you can mix them up and have, say, 8 out of 20 of them are red, and 12 out of 20 of them are blue, 1. You can have these coins, again, head could be 0, tail could be 1. These are all just arbitrary for the sake of argument. But then if you spin them, you don't know which side it's gonna land on. If it's a fair coin, you know you've got 50% of chance of only landing on 0 and 50% of the chance landing on 1. Then you see that, okay, for the quantum case, we're kind of playing with probabilities. So in the classical case, it's definitive. It's either 0 or 1. But then in the quantum case, you can allow to have these arbitrary, you could have probabilities of these two options. expressing them mathematically, then classical bit is just either 0 or 1, but quantum bits are a linear combination of 0 and 1. And these A and B here are the amplitudes for these two options. It basically says how much of your 0 is in your system and how much of the 1 is in your system. So A and B give you some weight of these possibilities. In our previous scenario, then you know that this field circle case, you will have a probability of 1/3 and 2/3 for A and B squared. Why are they squared? Because A and B are amplitudes, and amplitude squared are the probabilities. If you have learned physics in high school, I think you probably have learned about waves with amplitude, and then you get to prove that amplitude squared is probability. So this is very fundamental for quantum mechanics and quantum computing. But we don't need a lot of quantum mechanics. Here we're just using some fundamental properties of quantum mechanics in computation. So just look at the other examples. Your lottery bowl case would have A squared to be 8/20 and B squared 12/20. And your coin case is 50/50. Then what does this lead to? If you have one qubit, you have these two options, and each option will have a weight, an amplitude to them. And as I mentioned, A squared plus B squared, they have to, so the sum of the probability of the two options needs to add up to 1. And that's a common sense in a way. If you think about any probable event that's going to happen, and if you do any statistics, any probability involved, we have to have the total of all the possible outcomes to add up to 1, 100% of the case. So it's the same for multiple qubits. If you have 2 of them, you will have 4 different options you can play with. In this case, if you have 2 qubits, you could have 0, 0, 0, 1, 1, 0, and 1, 1. They're all possible, and you put them in superposition. And then again, you need the amplitude squared, sum to 1. If you have 8 qubits, if you have 3 qubits, you have 8 options. If you write down all of the options, that's all you get here. And each of them will have an amplitude associated with them. Again, you have to have this sum to 1. It's called the normalization condition in statistics. If you haven't learned that, don't worry about it, but this is kind of just think about any real events happening and the probability needs to sum to 1. So this, you kind of see a pattern here. If you have n qubits, you will have 2 to the n possible configurations in superposition. That's very different from classical case. When you have n bits, that's n bits. But if you have n qubits, you will have 2 to the n possible cases. So the number of possible configurations grows as 2 to the n. And if you want to use classical bits to represent qubits, you have to use 2 to the n number of classical qubits, and plus the amplitudes, infinite numbers of amplitudes that you need to represent a quantum bit, a qubit. So this amplitude here can be any number. It can be positive numbers like 1/2, 1/3, or it could be negative numbers. And in general, they can be complex numbers, so with imaginary parts. So in maths, you probably, I don't know at what stage you are with maths, but if you learn complex numbers, then these amplitudes can be all these general case. And we have a consequence of that. If we allow any number to represent these amplitude, They can be negative numbers. Then from our daily experience of amplitudes, say water waves, sound waves, light waves, we've seen, say, water waves, if you have two waves meeting each other, they can interfere. If you have the amplitudes in phase, in this case, they are in sync, they can add up. This is called the constructive interference. But you can also have, in this case, that the peak and the valley are meeting and they cancel each other out. This is called a destructive interference. We see this in all of the waves that we observe in our everyday life, and it happens in this quantum mechanical case too. So we are using that to do computation, and that's what interference comes in, that the amplitude sign, the phase of it is very important. So let's take a look at these two contrasts. In the classical case, so if I want to ask a question about probability, what is the probability of getting a sunny day the day after tomorrow? And I'm assigning random numbers here. Tomorrow could be half-half, rain or sunny. But then if tomorrow is sunny, I could have these two options the day after. Let's say 30% of being sunny and 70% of being rainy. If it rains tomorrow, maybe we are more likely to have a sunny day and then have some probability of getting rainy day again. And you probably already learned some statistics in math classes. If you want to work out this kind of conditional probability, you just time down the tree. What is the probability of getting sunny days in both cases? And we add them up. So this one would be 30 times 50%. This one would be 90% times 50%. You get 60%. However, if you have a quantum case, how would you represent the same information? We don't use probabilities directly anymore. We use amplitudes. Well, the amplitude, we still have the same probabilities, and we just need to square root them. If you take a square of them and you use the same numbers, but hey, we can have negative signs. For the sake of argument, I'm going to put a negative sign here and see what happens. Then you time down the trees again, but then this negative sign gets carried over. This is the interference, the destructive interference that this negative sign brings. It subtracted the possibility from this first case. And as a result, we get an even smaller number of getting a sunny day with an additional path of getting a sunny day. So that's what's very strange and cool about quantum, is that you could have this weird counterintuitive experience from what you would think classically, that additional path of getting something could even subtract it and destructively interfere it. It's not just theoretical, it's directly observed in real experiments. For example, this famous double slit experiment. I'm not sure if you have studied this in physics yet, but this is, if you do, probably the very first class about quantum mechanics would be about double slit experiment. And this is a direct manifestation of quantum interference. The setup is that you have a screen and you have two slits on them. And then you have an electron beam. It can be light beam, like photon beam too. So anything that is a quantum particle, you can shoot the beam towards the screen. Say you first block one of the slits. Then this is what you would expect to see. You will see a peak going through. The electrons will go through the slit, and you will have a peak there, have the most probability behind the slit. Then normally, and that's what physicists thought when they first discovered quantum mechanics, was that if I open the slits, we'll get both peaks, we'll get 2 peaks. But then that's not what they observed. That's not what happens. What happens is that when you have 2 beams coming out, that's like 2 water waves meeting each other. They can interfere, and then they have even this big peak after this blocked region because of constructive interference. And then on these other sides where you may expect more electrons to pass through, they can have a deep, they are destructively interfered. That's what's very strange about quantum system, and that's what's enabled by superposition of different probabilities, and they have phases to their amplitudes. And that's the #1 key concept that we would use in quantum computing algorithms. And another word about measurement, because we just mentioned measurement here, is when you do a measurement, it's not reversible. And it's kind of like this coin case. When you spin a coin, but when you measured it, it would have one probable result coming out. So then, for example, you have 4 possible states when you have 2 qubits, and you can do a measurement on 1 qubit, and you figure the first one is 0. And that means these 2 originally possible states are no longer possible, because you already made an observation and you know that the first one must be 0. So these 2 would then cancel out after your measurement. And then it tells you that the probability of getting your first qubit to be 0 is these 2 amplitude squared sum up. And then after the measurement, because you don't have these 2 terms anymore, it will be just these 2 terms, but then you will need to have a actual factor taking P into account, because you still need to satisfy that normalization condition. But not to worry about this too much. This is about measurements. And let's take a look at the other very important concept that superposition allows. Other than interference, we have something called entanglement. What is entanglement? Let's go back to our 2-qubit system. You have these 4 possible outcomes. And there's no reason we cannot have a superposition of any of them in superposition. So I don't have to have all 4 of them. I can have, say, this 2, both being 0, and in the superposition with both of them being in 1. And we have these arbitrary amplitudes here. Equivalently, we can also have the case where we can have the first one being 0 and the second one being 1, with a superposition with the first one being 1 and the second one being 0. There's no reason we can't do this. But then what does this allow us to do is that if you do a measurement on the first qubit, this is the first qubit, this is also the option for the first qubit. But if you measure the first one and found out that it's 0, then this one's not possible. It's not contributed from this state here. It is this state that contributes it. Then you know you don't even have to measure your second qubit in order to know that your second qubit must be 0. And similarly, this case is, take this one, for example, if you measure your first qubit, given that you already know that you set up the system in this option. If you measure the first one and found out that it's 1, you don't have to measure the second one to know that the second one is 0. This means that the 2 qubits are correlated. You can't separate them. They are not independent anymore. If you measure them, you will know the result of the other. If you have read or heard anything about entanglement, you probably heard people say that, oh, if I do change one of them, the other one would instantaneously change. This is a very misleading statement. That is inferring information can transfer faster than light. Like if you have two entangled qubits, if you separate them, you change one of them, the other one will feel it. That's not what happens. All is happening is that you know what the other one's result would be without measuring it, because they are set up this way, they're correlated. So don't get too fancied up by the science fiction type of claims. And all is saying that is that, well, it's a correlated system. So even if you separate them far infinitely away, you still have the system and you're not disentangling them, then this entanglement and correlation will hold. There's no spooky interaction at distance. That's a way that Einstein sarcastically described when he didn't want to believe quantum mechanics. But he made great contributions there. So it's a fun description, but then it's often get misquoted. And we can have this special arrangements with the equal amplitudes in front of them. And these 4 states are called the Bell states, named after Bell, a physicist. And they are just the same situation as I showed earlier, but with the equal amplitudes. Then what this special arrangement allows us to do is that we can even know the probability of getting the outcome. Say we have these 4 options. These are written in a shorthanded way. The first qubit, if you measure it to be 0, then you know you will get this 0, 0 state out with a probability of a half. If your first qubit is 1, then you will get this state out with probability of a half. So this is the same thing as I showed earlier, but with the same equal probability. And this Bell states turn out to be essentially very, very important in every single quantum computing algorithm. You want to entangle them and you want to use interference, you would need to use one of the Bell states. Okay, so entanglement can be very helpful in communication as well. In encryption, because if you entangle 2 qubits, you can infer the information of the other one with your own qubit. For example, here Alice and Bob can entangle their 2 qubits into one of the Bell states, and then they can separate them. They can each take a half of that pair, so 1 qubit, and they can go as far away from each other as they want. But Alice will know when she does a measurement and get either 0 or 1 out, she would know what Bob will get without even having Bob do the measurement or even communicate with him. So then you can think about encryption methods that can use this entangled states as your key, because you know what the other person would have given your measurement. And if you can entangle 2 qubits, there's no reason we cannot entangle multiple qubits. For example, this 3 qubits state is this arrangement is the maximally entangled state. So all 3 qubits are entangled. This is also named after 3 people and they have a special name. You can also have the general case is with n qubits, you can also have them entangled up. And they can be very, very useful in algorithms. And we can use them to our advantage, but also entanglement can be very dangerous. When you do experiment, you have to really carefully set up your qubits and isolate them very well so that you know what your states are at and what entanglements each qubits are doing with their neighbors. So you need to keep them under control and isolate them. But if you're not careful, if it's not perfectly isolated, then the environment can come in and start to entangle with your own qubits, and then that could really mess up your system. And that's what we call decoherence. It can be going from the state you want it to be messed up by your environment. And that also includes your experimental probes, where you have to do measurements, say at the atomic scale, all of your measurement devices are also made of atoms and quantum particles. They can come into your setup and then mess up your setup as you do the measurement. So when you build a piece of hardware, the qubits, you have to be perfectly isolating them and also taking into account the errors that you may introduce during the measurement. And you just have to be very, very careful. We'll look at some of the hardware examples later. A summary of all these concepts is here. 3 key concepts. If you take anything away, take this today, take this page away. You might have heard the qubits in popular science articles say qubits are 0 and 1 at the same time, but it's not very helpful. It's not really helping people understand what qubits are, but we've seen today that when we are talking about qubits, it is a linear combination of 0 and 1, and we are using the probabilities of getting either 0 or 1. And if you also learn physics, perhaps in, like I learned physics like a couple of decades ago, and even then we were looking at these old description, is the Copenhagen interpretation, that when physicists in 100 years ago discovered quantum mechanics, they didn't quite understand how to describe measurements. They thought we have all these possible states in superposition, but then when you do a measurement, it all collapses into one state. That is very old way of describing things. And people still use it right now when they teach quantum mechanics. But it's just an easy way out. It's not really explaining anything. It's kind of trying to hand-wavy say that just one state comes out. What's really happening, we've seen, is interference is happening. And what we are getting out of measurements is the most likely outcome in your whole system, because the least likely ones got distractively interfered. They cancel each other out. What we see in measurement are these ones that are constructively interfered. Then the third thing is about entanglement. I already mentioned that there's no spooky interaction and there's no instantaneously information transfer of the change. What's happening is that your entangled bits are correlated and you can measure one to know the other one without measuring it. Nothing super fancy there. We have a fact sheet where you can check a lot of misunderstanding in quantum computing, and they have a list there, which is quite nice. All right. We spent most of the time on this concept. Now we are moving on to how do we manipulate the qubits? How do we actually use it? So we're gonna look at a little bit of maths, linear algebra there. It's not very hard, it's linear, so it's not going to be really top level maths. And we're gonna use what you probably have learned already. So I think when we were very young as kids, we want to represent real numbers. We can draw a line. We have this x-axis and we can just draw anywhere on this line your numbers. So if you want to have a real number from 0 to 1, 1 will be this line here. It's in one dimension. But if you want to represent the complex number graphically, you can introduce an actual axis, and this would give you an angle and tells you how much of x and how much of y is in your number. This is a phase that you can describe the complex number with. And x would be the real part and y is the imaginary part. Now, if I mentioned that qubits can be described as a vector. How do you describe a vector graphically? Turns out you can use this sphere. So a sphere is by itself a two-dimensional object on the surface, but in 3D, you can see it as a sphere. It really just is describing two numbers. And this is introducing another axis here. So you have 3 dimensions. Now you can, again, draw a line, but this line now gives you 2 angles, a phi and a theta here. You can write trigonometrically to say how much of this vertical axis has. So how much of theta and phi you have for this projection. So you can, on this sphere, define what 0 and 1 are. In this case, we use the z-axis and have these 2 polar positions to be our special 0 and 1. And if you then write out the angles, you see, oh, we have this amount of 0 and this amount of 1. And turn out these are our A and B that we saw earlier. So that's how you represent a vector. It's not strictly just a qubit. Is any 2 by 1 vector, you can do that. And then we can use that to represent our qubit. So if we can put our qubit in any of these states, that means that it's anywhere on this sphere. So if you want to manipulate it, that just means that you just change the angle, you're rotating this vector on the sphere here and put it anywhere on the surface. And turn out we have matrices that can do that. If you want to manipulate vectors, you use matrices. And you have these 2 by 2 matrices, actually 2 of them. One of them is changing your angle phi. This is the angle that away from the from the x-axis. And another matrix that changes theta is the angle that changes your how far away from the z-axis you are. So if you apply this general matrices, you can put this vector anywhere on the sphere. Looks like a lot of cosines and sines here, but we're gonna reduce it down to some special cases that are simpler and we use all the time. So say that you want to move your vector, you want to change your qubit to any state you want. You are just changing the location of these vectors on your sphere. And here's an analogy. When you want to come up with any number, so you have this, money can be any real number, and we don't have a coin or a bill for every single number. We just have these 1, 2, 5, 10 that allows you to add them up to get any number you want. So this is kind of a set of simplified, short set of numbers that allows you to represent any number you want to get. This is, we use this kind of logic for changing the qubits too. We don't have to have all of these angles, but these are the general cases. We could have a set of gates or matrices that would allow you to go to some special places on the block sphere that we constantly want to use. So here are some special gates, and they're called universal set of gates, and there are different options, but I'm gonna show you some of the common ones that we use as the universal gates. First one is this Z gate. These are 2 by 2 matrices, and they have just using zeros and ones, sometimes with a face introduced. So the Z matrix or gate is a gate for you to change your vector and rotate it around the z-axis. So it's effectively changing phi by 180 degrees. So it allows you to do this rotation. So it's a special case of the 2x2 matrix I showed involving the phi angle there. You can also have a special case that allows you to rotate around x-axis, so that is changing theta, and it's just 0, 1, 1, 0. And what it actually does, we'll also try some exercises, but what it does is rotating, but also you see that 0 and 1 are on these locations, and it allows you to flip from a 0 to a 1, or from a 1 to a 0. So here are two important gates to remember. We also have another one called the Hadamard gate or H gate that's commonly used. That allows you to change from these 0 and 1 to a middle case. We call it plus and minus. We don't have time to now, but afterwards you should try doing the math and see to prove this, that if you apply an H gate to 0, you will get this state. And you see that it's a superposition between 0 and 1. So intrinsically, you could start with a classical type of bit. 0 and 1 are just special cases for a quantum bit. And when you do a Hadamard or H gate on them, you can actually put them into superposition. So they become quantum. So they are called plus and minus to be just a shorthand. So plus state and minus state. And this minus sign is important here, and that's also introduced in the H gate here from this matrix. It has this minus sign. We need that because without it, if you get to say plus and minus, and then you want to revert it back to 0 and 1, you won't be able to do that if you don't have that minus sign. You won't be able to have a one-to-one mapping. You won't be able to distinguish what state you are on. So that's very important that you have this minus. And we also have some other commonly used gates, and together they can be used as a universal set that allows you to put your qubits to anywhere on the sphere. This S gate is nothing but a square root of the Z gate we introduced, and it has this complex phase I introduced here. That is rotation around Z-axis by 90 degrees. And then we could also rotate them by 45 or 22.5 degrees. So you're just subdividing your Z gates. So that's a quick introduction. And there's one more thing before we go to the hands-on part. We were just talking about single qubit gates, but what if you have multiple qubits? So we have these control gates that allows you to control multiple qubits based on your system. So say this one is called a CNOT, control NOT gate. It's a 4x4 matrix instead of 2x2. And what it does is that it can allow your first qubit to be a control bit and your second qubit to be a target. And you can see that when your control bit is 0, your second bit doesn't change. But if it is 1, your second bit would flip. So that's what it's trying to show here is the control says, I will control you if I'm 0, you stay the same. If I'm 1, you flip. So from here, you can even see from the matrix that the first quadrant, nothing is changing. That's a identity matrix. But the fourth quadrant, you see, that's actually an X gate that we saw before. It's a flip. Okay, let's get to the hands-on part. Probably enough theory by now. We are using this quantum katas from the Microsoft Quantum team. This is a set of exercises that you can use for learning purposes to self-paced, run some code, and get familiarized with concepts. So let's take a look at the superposition exercise first. I will try to post the link here if I can find the chat. You can also find the, just by searching it online, quantum katas. I will try to increase the size of this. I know I'm sharing two screens at the same time, so it's quite narrow. Go to that link, and we will see that it's got all these folders on GitHub, and each of them is a kata. Each of them is trying to teach you a concept. They have simple ones like basic gates and superposition, and then they have more complicated, deeper level ones for you to self-teach and try later. So we're gonna go with the superposition. No installation needed. You just click on the Jupyter Notebook option. That will bring you up to the binder. There is also a local version too. If you ever run into problem into playing with this online, if your internet's too slow, you can also download it and run it locally. But for purpose of our workshop, it should work unless I'm using up my bandwidth. I will need to jump to the local type. Yeah, it's actually, as I mentioned, quite slow today. Can I do a technical check if you can hear me and you can also load this? Feel free to unmute yourselves.
I can hear you.
Okay, are you able to load the exercise on your own computers?
I haven't loaded it yet. I'm still on it.
Is it still loading?
Yeah.
Right. Let me try opening it again. Okay, mine's loaded up. Yeah. Let's try to do this together. I would let you try the exercises and also shout out the answers in the chat. So I would show you the tasks that we want to carry out today and do this together. This is the superposition kata, and it's got all these nice references you can look into. We have documentation to help you find information on the topics that we are trying to learn within each kata. So read them in your spare time. We're just gonna go to the task 1.1 here. So the first one is a free one. It basically tries to show you how this works.
Sorry, are you able to?
Yeah.
Are you able to remove the Q sharp exercise screen and just focus on the on the Jupyter, because the screen is very narrow and I don't know how much the students can see, just so that we just have your.
I see.
Because I can't see.
There's one thing I can also try is to change the. Sorry. change the resolution of my screen to make it not so narrow. Because I do need to refer back to this PowerPoint slide. Hopefully this works. And let's go back to Katos. Is it better now?
Yes, much better. That's
Yes.
yeah, now they can see
Okay.
much better. Otherwise, it was just half the screen.
Yeah, I would just flip between the two windows if I want to show you things. So this one is the free exercise. So let's see. Input is a qubit in the 0 state, and we want to change it to the plus state. And I actually just talked to you about what gate does this, and it tells you to type in HQ and do Shift Enter. That helps you run it. They already tell you what to do, and this is just to show you how it works. And it's nice because when it outputs the answer, it shows you what your state is at. These are the amplitude. This is basically square root of 2. And you can see that is 1 over square root of 2. You can see that they have equal amplitudes. All right. Now we have task 1.2. Okay, so we start with 0 state again, but now we're asked to produce the minus state. How do we do this? I'll wait for you to think about it, and I can also show you we have some hints in the PowerPoint. We just learned about X, Z, and H. Type in your answer, the first person who gets in the chat. No answer yet? I can show you the logic. So you are started with 0, but you asked to produce the minus 1. So from here to there. We haven't seen any single gate that can do that. We actually have to use multiple gates. You first have to bring your 0 state to a different state that can allow you to go to the minus state. And what is that? Is the 1 state. So how do you go from 0 to 1? You need a flip. And we have this flip gate here. So here, what you need to do is to first bring your qubit into, this should make 0 become 1. And then you do the each gate like in the first exercise. That should do it. Yeah. So I don't know how many people already do programming, and how comfortable they are with seeing coding. So this is a very high level language, so you don't have to worry about the details in your hardware, say, but you know that what you want to do to your qubit, and you express it exactly with the gates. And it's a very good language that is high level. Okay, let's try a third exercise from the superposition, the kata. So you are started with 2 qubits, 0, 0. And you're asked to set it to a plus plus. And don't get thrown off by this symbol here. Is called a tensor product, but it's really just showing you that there are 2 qubits and you can represent them in this way. So it just is the same as changing the 0, 0 to plus plus in this bracket. Any idea? I think I'm gonna leave the exercise to people to try later. And we have all these very nice set of self-paced learning. If you're interested, you should get into it to try to complete all of them. We have the quantum gates task. I can also quickly show you how that works. That's also an exercise that a concept that we talked about from today. Purpose of this exercise is to help you see how to translate your understanding from theory to implementing it. Oh, someone is asking something to do with the H function for the third exercise. That's from Sherry. Thank you, Sherry. Yeah, exactly. So it was exactly like what we did for the first exercise when we had the 0. But now you have 2 of them, you just apply a H to each of them. Exactly, very good. Thank you, Sherry. Let's go to the basic gates exercise. And we're gonna see more of these superposition states. The first one is, again, teaching you how to do it. This has a arbitrary state now, like what we saw before. We can have amplitudes alpha and beta, and they could be any number. This one is asking you to change 0 to 1 and change 1 to 0. And we actually just did that with just one option before. Now we're given an arbitrary state with 2 options. So there's nothing but doing a flip here. Hopefully I didn't get disconnected. I just saw the kernel. Yeah, okay, that works. Yeah, so that's exactly what it's telling you to do. Xgate is helping you flip between 0 and 1. And probably another visual that can help you is like this. We can have these poly gates. They are the X, Z gates that I mentioned earlier are named after physicist Pauli. So X has 0, 1, 1, 0, and it basically flips your two options. You could, if you can rotate around X-axis, then you could rotate around Y-axis too. So we have a Y-axis matrix that also flips, but also adding these phase in front of the amplitudes. And Z gate we have already seen. It just does nothing but adding a phase minus to the second amplitude. And in general, you can use a general rotation that I already showed with angles. And turns out that, so you can write X, Z, Y all in this general angle, and you find some cases you have 180 degrees, sometimes 90 degrees. And this here also shows that you just have to have these two, because the other option is, it can be described by a combination of the other gates. So, because here you are just trying to change two angles, so you just need two matrices, and the other one can be described. So let's go back again to the second exercise. Now we have a qubit, again in arbitrary state. Oh, sorry, that's what we already did. This one. And then it asks you, if the qubit is in 0, change its state to plus. If the qubit is in 1, change it to minus. Didn't we see this earlier? So I guess that's not super challenging, because we just did the superposition exercise and we have a gate that already does that, and Sherry already put in the chat that something to do with H for this case too. But we're just given a general case now with this arbitrary state. So this H would automatically allow you to go from 0 to plus and 1 to minus if you're given an arbitrary one. And this is trying to show you how these arbitrary gates changed, how much amplitude of 0 and 1 you have in your system. Let's try one more, and then we're gonna talk a bit more about the concepts. This one is asking you to add a minus to your second amplitude. Does anyone remember which one we just saw that does this? Allow you to think a bit. So this is why I wanted to have two screens, because I want to put them side by side. Now it's a little hard to. Anyone see the pattern here? Want to put in the chat? Try it on your own katas. Another technical check, are people running the katas? Or they're just staring at the screen?
Guys, can you confirm if you're actually doing the exercises?
Yeah, I see people putting, very good. Thank you, Rachel. Rachel says is the Z gate. Let's do that. Yeah, very good. We got the result out. And this one is actually quite funny because it is asking us to have a minus sign for the second one. And we know that the Z is giving us what we wanted. But there's no difference if we had a minus sign in front of both of them. And we could have an amplitude that comes out with the first one having a minus sign. So this one is the desired state, but the actual state it outputs gives us the minus sign for the first one and a plus sign for the second one. However, it is still correct. These two states, when you measure them, are equivalent. So this is run on a simulator where it tries to simulate a real quantum computer when you're trying to measure each qubit to get its amplitude, to get the state out with a certain probability given by the amplitude. So we know amplitude squared is the probability. So when you're squaring them, this minus sign doesn't matter which one you get it from. And this is showing us we actually, if we have a minus sign for added up to both of them, you will get this, which means you're adding a global phase, a minus sign to both of them, and it doesn't really matter. So you actually can run this several times on the simulator. At some point, you may get the right answer. It's trying to behave like a real quantum computer. So I have done this before, that if you try run, now you can, for certain times, it will output like this one, and the certain times it will output the opposite case like we saw earlier. So this is demonstrating the actual behavior of a qubit. It's very cool. So I think we now just have a little bit of time to talk about some other things, and we're gonna wrap up soon. Definitely try the katas on your own. And we also have the documentations that can help you get the answers that you will need to get to your understanding. So I guess the slides I can share with you, we have these links to the Microsoft Quantum Computing documentation, and some of the exercises we need certain libraries that we need to put into the answers. And there you can also find a lot about the concepts in quantum computing and learn about them and try writing your own algorithms. Let's just take a quick look at algorithms now. Because I have been constantly saying that these three concepts are very useful for running algorithms. They do definitely show the real power of quantum computing when we are using interference and entanglement. If we don't, then we don't even need quantum computers to solve some of the problems that classical computers can already solve. So quick, this development for algorithm is pretty new. It's been a few decades, but from the 80s, that's when the quantum computers, machines that may use quantum mechanics, that was when it was proposed. And in 1985, when Deutsch proposed a quantum Turing machine, and he thought that we can show that we can build quantum circuits that are universal. And he came up with an algorithm that called the Deutsch algorithm, and also collaborated with Hose, called Deutsch-Hose algorithm, that demonstrates a particular use case for quantum interference, where you can do a task faster than a classical algorithm can do. But it's not a very useful, it's not being used and applied in any problems, but is a very good demonstration for learning purposes. It's simple enough to show people how interference can work. And then Peter Shor came up with an algorithm that can do really large factorization, factorize large numbers efficiently. This is very, very useful because we have been using a cryptography method called RSA, and that relies on really large numbers being very difficult to factorize using classical computers. So we are essentially using this inability of classical computers to encrypt messages. So timing numbers are easy, but then factorizing a really large one to its prime factors is very difficult for classical computers. But quantum computers, because it uses interference and entanglement, it can actually solve this problem very easily. So then that's why it's very dangerous, and people are scared of it in a way that it's going to break all of our encryption. And we have to come up with better algorithms to counteract this using quantum computing. If quantum algorithms going to break our current method, then we better come up with algorithm that we can do better encryption. Gruber's algorithm is also a useful one that also has been used in cryptography. You can come up with a lot of interesting applications for it. It does a search of certain items in a unordered list. Say, let me just use Groover's as an example. You have a very disorganized library, and you have all these books randomly organized, not in alphabetical order or any way. You have a book you want to look for, you have a title of it, but you kind of have to go through all of it to see which one it is. If you're running it classically, you have to look at each title. If you're lucky, maybe the first one is the one you're looking for, but if you're unlucky, you have to go through all of them, and maybe the last one is the one you're looking for. But Gruber's algorithm takes all of these books, titles, feed it into your algorithm, and these titles from the books that you're not looking for distractively interfere in each other. And you have this book that you're looking for getting amplified every single time. You feed it, feed the titles through several times. And then at the end of the day, the signal from the book you're looking for would pick up, is increasing, amplifying the amplitude of this one particular item. That's what Gruber's algorithm does. But one note of that is that we still have to know how many qubits is needed to run this algorithm to do anything really useful. So when you have n qubits, when I described that you can put all of the books into this algorithm and run the algorithm to square root of 2 to the n times to get your answer. In the classical case, you have to do 2 to the n times. So in this case, then Gruber's will be faster than the classical one. But this speed up will not really show up until you have a certain number of qubits built. And this number here is allowing you to see that Gruber can take shorter time than classical one. Because you also have these factors in front of them. Intrinsically, you have to have the classical algorithm doing this task and Gruber's algorithm doing this task. Intrinsically, running each time is going to take certain time. So it's not a speed up from the very beginning. You have to have these factors in it to really see when classical is going to take longer than Gruber. But the thing is that this number here could be a really large number. We have to build a hardware quantum computer that has enough number of qubits to do this algorithm. And it's kind of a race between supercomputers and quantum computers. In this region, you still have the supercomputer faster, but then at large numbers, when you have very complex problem, quantum computer can surpass. So here is a very interesting region for all of us. If you're learning, starting to develop in quantum computing as a developer and researchers, we are trying to find other algorithms that show speed up for quantum and over classical with fewer qubits. That's why we need a lot of people from all kinds of backgrounds developing and try to find even more useful algorithms. So here are just overview of a lot of the algorithms that are using interference and entanglement. We will not go into details of them today. And you see all these kind of circuit diagrams. These are simplified circuit representations to let us visualize how qubits can interact. So I show you the block sphere, this three-dimensional sphere that's describing one qubit, but it's not going to be useful when you're trying to describe more qubits because you need multiple dimensions. When you have multiple qubits, you can draw them as lines and see how they interact. These are the circuit representations, and you can draw all of these gates in terms of circuits, and they have the corresponding matrices. We won't go into details today, but one note of that is that if you come across circuits, they are only useful for a small number of qubits. If you want to solve just for the sake of learning, perhaps you try it, and with a small number of qubits, you can draw the circuits. You say, oh, okay, I understand it now. But now, if you want to run a really big algorithm with so many qubits, like millions of them, you won't be able to draw all the qubits, and you won't be able to draw the circuit. That's why we needed a language like Q# that I show that allows you to code things up at really large scale. Just a word of that is like you have Pythons, C#, and F#, all kinds of computer languages, Java. You can build websites, you can write your own apps. When you do that, you don't even need to worry about how transistors work at the very basic level. Similarly, for quantum computing, we also need language like that to allow us to write our applications without even worrying about the individual qubits. That's what Q# can do. Now, a very last bit is the hardware. It's a pretty crash course for everybody. I guess there's a lot of information for you, but I think hardware is very interesting. It has, it really requires the fundamental condensed matter physics knowledge to build one, but we should show you the general concept. Because when you learn about the theory, and then you learn about the algorithms and applications, and you're gonna wonder, how do we even make a computer? How do we even make a qubit? Going back to our transistors I showed earlier, that's made out of materials, and you're using this electricity in your materials to represent zeros and ones. But now you want to have a system that allows you to have a superposition of 0 and 1. You have to find some natural materials or artificial materials that you can construct to behave that way. A natural substance you could use to have a qubit, to make a qubit, could be the electrons. You may know that electrons have spin. You can have spin up and down. Maybe you can use those two as your zeros and ones, because we know spin up and down are intrinsically in superposition, and you could leverage that. But then trapping electrons are very difficult. You have to confine it into something to isolate them and manipulate them. So there are several ways to do it. And these have all been done in labs and some scaled into production level. So one of them is the quantum dot, which is again using semiconductors, material layers of them. You can put two semiconductors next to each other and form this region of electrons that's strictly in 2 dimensions. And then you can apply some gates to it, and you can actually remove electrons under the gates. Eventually, you remove enough electrons, there's only one left in this region. And that's what's called a quantum dot. Is an artificial type of architecture we make. With smart people, we are able to make structures that can trap a single electron inside a piece of material. And you can then manipulate, you can shine light on it, you can apply electromagnetic wave to change the spin of the electron there. And that's how we can apply gates onto these physical systems. Similarly, you can also use crystal structure to trap electrons. This is a crystal lattice, is actually diamond, is all carbon, and each carbon has 6 electrons. If you look at the periodic table, you'll find nitrogen has 1 more electron, it has 7. You can remove very carefully one of the carbons out and form a vacancy, and then replace one of the carbon with a nitrogen. And now you have this extra electron here that's bound by this nitrogen vacancy region. So that's your electron there you can manipulate. It's quite cool. But then electrons are not the only thing that has spin. We can even use ions. Ions are atoms with ionize by removing or adding electron onto a neutral atom. So it has a spin and a charge to it. You can trap all these ions into an electromagnetic field. This is what is trying to show in the cartoon here. You can have all these spins align with your magnetic field, and you can shine light on it, because light is electromagnetic energy that can push and manipulate your ions, so you can flip spins. It's a little bit more complex than that. It's a very hand-wavy, simplified picture. It's really trying to use 2 of the energy levels that's in your ions. So you can have these different types of ions with their intrinsic energy levels where electrons can occupy. And you can form things like fine structure and hyperfine structure. If you get to learn physics later, you will learn these concepts, and these have energy levels for electrons to occupy. You can pick 2 of them. You have a lot of them to choose from, but you can pick 2 of them as your 0 and 1s. And then you can, because they are already in superposition, you can put them onto any of these and manipulate which one is occupied. But if you can trap ions, we can also make artificial atoms or ions to mimic how particles behave. You can actually fabricate electronic circuits very, very small and cool them down using our nanotech technology, our micron-size fabrication, to make LC circuits, so capacitor and inductors. I don't know if you've learned any electrical engineering or physics concepts for electricity yet, but you can make circuits just like your battery with a light bulb. You can have capacitors and inductors, and you can form an oscillating circuit there. So the electricity in there is oscillating. And then you can form a oscillated energy level for your system to sit on. So if you're in a classical case, classically you can have LC circuits, and you could have a oscillating energy profile. But this is a superconducting inductor. I won't go into the detail here, but when you have a superconducting inductor, you could change this energy to this shape. And if you cool it down to very cold, you can bring this circuit from a classical regime to quantum regime, and then you are starting to have this energy level splitting. And that's why it's called quantum. It means a packet of energy, a level of energy. And you are splitting your continuous profile into discrete energy levels. And then you can pick two of them to be your zeros and ones. So I know that this has a lot of perhaps not so familiar concepts introduced. But later on, if you start to learn physics and start getting into electrical engineering or condensed matter physics, you would understand all these. Don't worry about it. Just trying to show you different ways qubits can be made. There's also other types of particles and quantum objects you can use, like photons. Photons are light particles. You can guide them, like I mentioned in the beginning of the talk, when I was working on silicon photonics at Intel, is to guide light on chip. You can actually make waveguides, shine light on it, and then guide how your lights propagate on the chip. You can make all kinds of structures and be able to even embed your zeros and ones into different polarizations of light. So in this case, then you have not electrons, not ions, not artificial atoms, but you have these different polarization options for you to put your zeros and ones into. That's another option. And there is a very final option. There are actually a lot other more, but I'm showing you some of the ones that's being used by industry, big companies. This one is called a topological circuit. It's being developed by Microsoft right now. It's a very different type of qubit that we're making. It's not relying on individual particles, electrons or ions, is relying on the many electron interactions. When you have a lot of the electrons putting together, and they can behave in a collective way, and you can shield the system from a lot of the decoherence noise that I talked about earlier, that you have to set up your system carefully so that it's isolated. Because when you are looking at individual electrons, it's very easy to mess them up. But if you're relying on a collective interaction between them, they can actually be immune to the environmental effect. And this is an architecture where we can put nanowires on superconductors to form some specific modes for electrons to occupy. And we can have zeros and ones when we have these two modes at the end of the nanowires being occupied or not, to be our zero and ones. So a little bit abstract for people looking at this at the first time. But the topological type of qubit is the least error prone. That's why we're pursuing it, is that it can have very good payoff, but it's very hard to make. So the other ones, some of them already are being used in quantum computers, like the trap ions, the superconducting circuits. but we are pursuing this one because it's the least easy to get messed up by environmental noise, and that would allow us to go to a really big number of qubits if we get to get this working. So that's a very quick overview of the hardware. So for anything that you are not super clear about from this workshop, don't worry, we have more detailed classes. I've been teaching at Hackaday using comics for quantum computing, and actually today is kind of a condensed version of a lot of the lectures that I gave before. So every Sunday I give this 30 minutes class only discussing one concept. So it's not feeding you too much information at a time. So it's much slower, and we take a deeper look at each concept. And we use this Microsoft Q-Sharp documentation for exercises as well as the quantum katas that you saw today. So if you're interested, definitely start from the beginning and look at some of the recording that's already up on the internet. Also, Microsoft has produced the MS Learn modules. That's actually part of my job, is to make these learning materials for developers. MS Learn is a learning platform for self-education, and we have just started the quantum content there. So right now we have 2 modules you can take. If you want to become a quantum developer, definitely check those out. We have one about using the quantum development kit, writing your first Q-Sharp program, but probably not your first one because you tried already some Q-Sharp today. And then we'll have another one on quantum-inspired optimization. So that's on something more on the classical algorithm, but inspired by quantum. We can also have interesting applications there. Any questions for today? I think we still have some time for people to ask questions here. If you have further questions anytime during your study, through your own interest reading, feel free to reach out to me and post your questions on the Hackaday project. I will ask Elena to share the slides and the links with you. If you want to watch any of the recordings, they're also on Hackaday, but you can also look up on my YouTube. That's it for today. I know it's a lot of new content for people here.
Thank you so much, Kitty. And that is quite a lot of information. So I don't know how everyone is doing. Do you want to unmute yourself and tell us where you are? Do you have any questions at all? Feel free to just unmute and ask your questions.
So sorry. Do you know for the hardware that you use for quantum computers, is it mainly made up of like chemical substances, and how does that kind of like translate into like actual functioning of the computer?
Yeah, so they are all made of materials. They're solid state materials, so they're not, I don't know if there's any like liquid or gaseous types of qubits, but these ones that we have built, even being used, are all made of solid materials. I guess the irons are more like isolated from the rest of the material, but you still build them into compact electronics. So yeah, so they all have different ways to be manipulated. So you're asking how they can be translated into these gates that we talk about, for example. So all of these electrons, ions, even circuits and photons, this is more multiple electron collective interaction. They can be manipulated with electromagnetic waves. And that could be at any frequency. That could be any form. They could be light, They could be electricity that you pass through on your circuit. They could be microwave. They could, so any type of electromagnetic wave you can use to either shine it on them or pass electrical current through your on-chip circuit in order to change the state of your qubits.
Okay. Also, is there like a specific electromagnetic wave that is most useful, or it depends on the type of computer?
It depends on the types of computer and at what frequency they are responsive to.
Okay.
Yeah.
Thank you.
Thank you.
Right. Any other questions at all? And Effie, you're studying physics at Imperial, am I right?
Yes, I am. Yeah.
Awesome.
Yes. So that's another quantum girl in quantum to be. Well done. So anyone else who would like to ask a question? Not yet, but perhaps I could ask you a couple of questions, Kitty.
Yeah.
I would love to know where do you see quantum computing make the most contribution in the future? What is the future with quantum computing, particularly in the AI for good space, or for impact? We would love to know.
Yeah, there are basically 4 application areas. I mentioned some of these before. So here are some problems that quantum computing can be useful for. But if you look at the areas that will include simulations, namely these chemistry, material simulations, biological simulations, so all of the interactions that we rely on quantum mechanics for simulations like that. So then these things can be applied in pharmaceutical, oil and gas, agriculture, all kinds of industry. And we also have cryptography, so information security, that like banks and governments, everything that's relying on security is got applications there. We also have optimization, so like logistics shown here, or signal processing. We need a lot of optimization. How do you route traffic? How do you organize your city? So a lot of the application areas. The fourth one is machine learning. So that might be the most maybe similarly closest to AI.
Yeah.
In the machine learning area, both machine learning and quantum computing are still developing fields. And we see possible combinations of the two, and there are some problems probably gonna be easier to solve on a quantum computer for certain machine learning algorithms. I would encourage you to look into our documentation. We actually have a quantum machine learning library. Let me show you where it is. Oh, I think I stopped sharing my screen. I need to turn that back on. If you go to Microsoft quantum documentation, it's a very nicely organized documentation page. Actually, I managed it, so I shouldn't have posted about it. But yeah, my team does a lot of great work on this. You can find a lot of the concepts and how to install, how to develop, and there are tutorials for you to try these algorithms and samples in the Q-Sharp libraries. Under the Q-Sharp user guide, you find these different libraries like chemistry, machine learning, numerics, this probably will be very interesting for you all, is to look at some samples using machine learning, using quantum computing for machine learning, and take a look at where the state of art is. Right now is still very early stage. People in industry and academia are all working on how do we leverage two together. So yeah, definitely keep an eye out on this area. Will be very exciting.
Very interesting. And Kitty, so in AI, we do have some ethics boards, and we emphasize ethics every time we develop AI algorithms to be mindful of what might go wrong. Is there an ethics board or some ethical concepts developed alongside quantum computing already? Is there anything we in the future should be mindful of, or fearful of? What can go wrong with quantum computing?
Yeah, I definitely think we need, because we need to, any technology can be used for good and bad. And I think it's a good time to start doing that. Internally, we have discussed, we definitely want to apply our technology ethically. Yeah. So for all of the case studies that we do and all of the applications that we do, we are really mindful of that. In terms of the industry in general, I don't quite know if there's any established standard organization, and I think there needs to be. So very good point.
Excellent. And sometimes I hear AI being sort of compared to infancy, sort of age 6 or something like that, or even younger. Where do you see quantum computing is right now? Is it like baby age 1, age 2? How old do you think in terms of the capability, like some people compare AI to?
I'm not quite sure about this terminology, the mapping here. I'm more familiar with the startup type, like H1, 2, and 3, like Horizon 1, 2, 3.
Yeah, no, I'm talking more about infancy in terms of can we really realistically do much with quantum computing at this present time, or is this only speculation or generalization in terms of what quantum computing can achieve right now?
Yeah, so a lot of the current use cases that already we are applying in industry, more on the side of optimization. Those are quantum inspired applications. Okay. So we are still running algorithms on classical hardware, but we represent the problems in a quantum mechanical way. Is kind of inspired. It could be a classical problem, like a logistic problem, but we can represent it with matrices, and we can put our data in a certain way to get speed up in the optimization. So that's already being used. That's already what people can try hands-on. And what we have made available are also the cloud service that we can allow people to run algorithms on their own computer, then connect to actual hardware through the cloud. It's called Actual Quantum. So a lot of these current problems are done this way. If you are a industry customer, you can already access it. It's currently in private preview. So people can describe their problems in a quantum inspired way and already solve their problems. In terms of running the hardware, quantum hardware and quantum algorithms is still a little early. And I think there are, as I showed a few examples of the algorithms, they are still quite academic. So we understand these algorithms, but we don't have the hardware yet to really run them. So the whole industry is working towards that goal and also coming up with new algorithms that perhaps can be used to smaller number of qubits or to run on the current hardware that we have available. So that's, yeah, the also adoption of quantum computing is gonna take a while for any industry, especially traditional industry. When they adopt new technology, it's gonna take a decade.
Yeah.
So I think right now is a perfect time for learning to understand this new technology before it's too late, when people are already using it, and then because it's a gradual adoption, and be left out from this.
Amazing. Does anyone else have any questions? Otherwise, I will just keep asking perhaps my last question then. So in 10 years then, Kitty, what are we going to expect from quantum computing then? Let's say in 10 or 15 years. Will it be adopted by enterprise, or do you see this becoming perhaps a subject taught in schools? Because this seems to be like it's something that young people should be aware of, particularly this generation.
Yeah, definitely.
Yeah.
It's already been taught in school, in universities.
Mm-hmm.
We have quite a lot of courses that we have a curricula that we already deliver and have professors teach them, and we also teach students in schools. So yeah, definitely is something that young people need to be aware of and understand. In terms of adoption, I think a lot of the industry would start to use them, because right now it's already being used, like the optimization cases that it's already being used by big companies. But there will also be academic research implementations. A lot of the very cutting edge research needs really heavy computational capabilities. The quantum computing can support that way.
Mm-hmm. And as consumers, will we see a variation of a quantum computer on our, I don't know, on my desk, for instance, or in my hands? Will there be some variation for ordinary people?
Yeah, so I think quantum computers would more be used in infrastructure, like our data center, where you don't have a data center in your home, but you're accessing it every single day.
Yeah,
you're using the internet and you're sharing data. Quantum computers probably gonna be very similar, that in certain locations we'll have that and people can use it through the cloud. And one thing I didn't mention is some of these architecture, some of the hardware are very difficult to build, because they need to be cooled down to very low temperature, and they have to have very delicate optical setup, or any electrical setup in general. So it's not something that people can really have the money or the capability to build at home. But perhaps later on in the future, we're shrinking things down smaller and smaller, and our first computers were gigantic too. Yeah. So yeah, at some point, maybe we don't have to cool them down. We don't have to make them so big. So that's gonna be a while though.
Yes. Okay, cool. Anyone else? Do you have any questions? If not, we can probably close this session. And Kitty, we're really grateful for your time. Thank you so much. If you share with me the links or the deck, I will post it in our Discord channel for everyone who was unable to attend this workshop, run through your slides. And I will encourage everyone to also check out the page where they can, learn about all of this at a slower pace.
Yes, I just wanted to show this, all of the slides you can find, and also the links to the existing recording. I wanted to show people I'm also giving people a certificate if they finish the kata, any of the kata. So I just had this here. So have a couple of certificates. When people complete kata, they can tweet or share on LinkedIn at these handles. And then I will give people some vector graphics that they can use to print on anything. So it's really great. I already got a lot of people completing that and then sharing with me. They print it on their mugs. So
amazing. Yeah. Oh, that's fantastic. So guys, everyone, you should definitely try them. And yeah, show us what you've tried, and Kitty will send you the certificates and stickers, and yeah, sounds amazing. So thank you so much, Kitty. So everyone, thank Kitty for her time, please, as well, as a matter of courtesy. And thank you so much, Kitty. We will be in touch with you, and we will let you know what kind of projects teenagers will be completing by next Friday. And awesome. You will probably hear, on social media and whatnot. So thank you so much for your time, Kitty. Thank you for tuning in. Have a great afternoon, everyone. And you too, Kitty. We'll be in touch soon. Bye.
Good evening. Good luck with the projects. Thank you.
Thank you, Kitty.